Hello everyone and welcome to the last installment in the While True Learn series. Today we're going to be looking at RNNs and LSTMs and talking about them a bit. So let's get right into it. If you haven't been following so far, basically this is the last step in this machine learning engineer's journey to try and translate his cat sentences. So recurrent neural networks, basically the way that they work is they try to guess what's going on within a given sequence. They're made for analyzing sequences instead of one element at a time. That's where the recurrent portion comes in, is that it will actually remember and take into account context. And that's why we have to hook up all around the RNN layer during training and during inference too, is it's re-going over everything that it already went through, just the same as it does in real life. And don't worry, we're going to go over a bit of, what are the weaknesses and what can we do to make it better. Here's a weakness, the vanishing gradient. This happens a lot of the time, and it can make sense why this happens through just basic math. And I'll go over this during the actual solution, but in any case, there were a couple of things invented to get around the vanishing gradient problem, the LSTM and the GRU. And the actual model that we're going to be building today is an LSTM. What the problem is, though, and I'll write something to show us this too. It'll illustrate it a lot better. But basically, when you multiply a number by another number less than 1, like let's say you're using a sigmoid activation function which squishes everything to in between 0 and 1, or a softmax activation function which squishes all of the probabilities so that they add up to 1. Multiplying a number by another number less than 1 will make that number smaller. And if you keep doing it over and over again, it'll get smaller and smaller and smaller and smaller to the point that the gradient vanishes. Another similar problem that RNNs can have is an exploding gradient, which is the opposite, where if you multiply a number by another number larger than 1 and keep doing it, that gradient will get too big to measure. And this especially represents a problem when you're doing math on computers, because computers end up representing numbers that are they end up representing floats a little bit weird, where 0 is viewed as the middle, and so 0.000001 is a lot easier to represent than 1.000001, which makes it easier for the computer to actually represent those smaller numbers and do that multiplication out to a lot more decimal points, which makes that vanishing gradient problem a little bit even more easy to run into. And we're going to go over that today, actually, with the importance of representing your data correctly. Video games reviews. I posted about this on LinkedIn not too long ago, but I swear if I see another NLP profile that does the IMDb movies review database, like, I'm just gonna die. It's not that that's a bad thing to do, it's just become so ubiquitous that you may want to do that for yourself and then go grab even just another data set. Do the same algorithm, but on a different data set. For computer vision, that would be like the Iris dataset or the MNIST dataset. For regular machine learning or like regression, that would be like the Boston housing dataset. It's classic. Everyone probably should do it, but my gosh, just it's too much. Making sure to have those organized really well. We've talked about this before, but I think one of the coolest things about this game is the whole timing that the Luden.io engineers came up with. It's really, really cool. Like the time to compute is so important in this game. You'll notice over on the left, there's a really cool thing going on where 3 of the numbers are blue in that input stream, as opposed to the whole string being blue. This is supposed to be representative of how far the recurrent network actually looks back in a given sequence, and this should make sense intuitively that you can't look at the entire sequence if it's really, really long. And so most people will do a thing called truncation, where they'll truncate how far back the recurrent network is allowed to look. We've come up with a couple of things to get around that issue, where like transformers, for example, are able to look at longer sequences than LSTMs or RNNs. One of the main reasons for that is because of attention, or the idea that looking back at the entire sequence, you only give your full attention to some of the things in it. It's a really cool breakthrough, attention and the transformer architecture. And if you're interested in learning about that, that's one of the things that I use for my job a lot, really, really often. And I'm doing another video series on those and explaining how they work and how to use them and why they work and how to make them better. And yeah, if you're interested, feel free to check that out. I'll make a little thing to look at it. But that's it. That's the whole game. So the cat starts speaking freely after the sequence is interpreted by the RNNs. I kind of wish that they had a companion game that was for actual engineering, instead of just the software engineering part, where you're making the recurrent neural network. But I would love a game teaching how to make a device that you can just put around the cat's neck that can interpret that audio in real time. That would be really, really cool. And so this is the cat talking to the engineer. There we go. Let's start explaining that vanishing gradient problem. Okay, perfect. So we're going to import 2 things for this. NumPy. I have a friend who recently said that he figured out why data scientists love Jupyter Notebooks so much, and it was he renamed this to PLT, and he renamed pandas to NP, and he renamed pyplot to PD, and ran it, and then deleted his changes so it looked like this again, and just watched the hilarity ensue. If you ever want to play a trick on your data scientist friend, that's a fun thing to do. Anyway, so what we're going to do here is first we'll look at the sigmoid, that one that I talked about earlier. This is a common activation function in shallow neural networks. Lens space. And we're going to have it go from -5 to 5. And I recommend you mess around with these numbers to see how it actually changes the sigmoid. And we'll just do the straight math. You can import sigmoid from sklearn, but I'm hoping to import the lowest number of things for you guys so that you can see like how the math is actually working out and it's useful. We do a NumPy exponential, -x. Ooh, I'm not outside of my parentheses. Cool. And here is our gradient function that we're going to use. X times 1 minus x. And then we're going to plot it. X and activations. Sigmoid steepest point. And you don't you technically only need to do the plot. You don't need to do all these labels. This is just so that you can remember what they are. Input data. Sigmoid X. Oh, that was a slog. So x10 equals 0. y10 equals sigmoid x10. So this is essentially we're adding a tangent line so that you can see what it looks like, what a straight line looks like here. It'll just help with the visualization. 10 equals np dot blend space x10 minus span x10 plus span gradient tan equals sigmoid gradient tan equals y10 plus gradient tan times let's do this data tan minus x. Color equals orange. True. Going to do a dotted line. And then we'll show it. No, we should do this orange too. Cool. All right, so this the sigmoid's steepest point, as you can see, is right here in the middle at 0. And right here in the middle at 0.5. That is the steepest point of the entire sigmoid. And you can see it really flattens out at the top and at the bottom. So these are the vanishing gradients that we're talking about. It's less crazy when you get to the top because you're multiplying by bigger numbers and it should get smaller and smaller and smaller because all the numbers are in between 0 and 1. But it is a lot more crazy as you get closer to this side and this origin point, that 0, 0 on the graph, because it will just get smaller and smaller and smaller and approach closer and closer to 0. And the reason this is a problem is because in machine learning, which is feature-based, we're trying to measure the difference and the relative difference between certain features of our data set and our inputs and our outputs. When those comparisons get smaller and smaller and smaller, it essentially tells the machine learning model that these things are not that different, even if they are. It's just further down in the sequence. So let's keep going here. this time we're going to do our x values and our sigmoid, and then a sigmoid gradient that we can see. So plots, and it'll be 1, 3, fig size equals 15, 4, char x equals true. Nice. Plot xx, and we're gonna write this once and copy it twice, and then just change things. Dot set title x values. I'm just gonna copy this. Dot set fucking type. Y not scale label. Y equals x. It's just the identity function. Dot set x label. And this is x input data. Okay. Hitting Control B instead of Control V. Alright, so let's change all these to 1s. Change all these to 2s. Awesome. And then for this one, X and activations. These are going to be sigmoid, sigmoid. I'm just going to copy it. Gradients. Okay. So yeah, this is essentially showing for this graph. It's just explaining this graph. We have our identity function with 0, 0 right here. This is the values that we're putting into x that are being activated by the sigmoid. This is your regular sigmoid with the top really close to 1 and the bottom really close to 0, but never actually quite reaching it. It's asymptotic. And then this is our sigmoid gradient, which this is the reason why this is an attractive function for statisticians, is it looks a lot like a bell curve, a normalized distribution, and so it's easy to use it to essentially normalize what's coming out of a model, so that it's predictable and you can do stuff with it. So let's then look at what happens when that gradient gets compressed, which hopefully this is interesting. We're going to look at the gradients again. Just do that. pt.legend. Location is up left. Limit our y to that same space we had before, which is essentially -5, -0.5, no, 1.5. The reason for this is it looks a lot better zoomed in. We'll do, I'm going to comment this out first, and then I'll show you what I mean. So here's our compression, right? If we then uncomment this, it zooms in on the important spot right here. So this looks more dramatic. It's exactly the same. but it helps visualize this. So we're then gonna just copy this a bunch of times and print a whole bunch of things. I'm just gonna copy and paste this. I don't need to be writing out print statements. This is all. So the max of our x data is it's 5, min is -5, so same scale as before. Max of sigmoid is almost 1, min of sigmoid is almost 0, and you can see that right here. It's that orange line, and then that sigmoid gradient shows the actual slope of the sigmoid at any given point, where right here at that 0 marker, it is the highest of the entire point. And you can see that the max of the sigmoid and the min, or the min of the sigmoid and the gradients is actually the same. But the difference in the gradient is a lot smaller. This gives it a lot of opportunity to vanish. So to kind of illustrate that point that I've been iterating a bunch of times, that like when you multiply numbers by other numbers that are smaller than 1 multiple times in a row, it gets increasingly smaller. Let's do this. So n equals 5, and then x equals 0. Change this, see if I'm right, see if this continues to happen. So the gradient equals sigmoid gradient sigmoid x. B dot range, or a range 1 n plus 1. Here we're going to do f strings. Scroll down so I can actually see here. Sigmoid x and then 0.5f. So if you're not familiar with this, that means I only want it to go to 5 decimal points. Should be the whole thing. Let's do a new line at the end of that so that we can keep track of these. Int loop, so we can keep track. Now is equal list, empty list, equals 1. We're gonna do times equals no. Times gradient. And then vals dot append total gradient print step s total gradient. And just add a little space there. Steps, vals. If you're interested in machine learning or data science, and this is boring to you, I have some bad news. Nobody cares about math or data science really if you have no way of visualizing it and explaining it. So becoming familiar with matplotlib and other ways of explaining the complexity of what you're doing and actually tying an image to it is really, really helpful. Even if you are a genius and can visualize it perfectly in your own mind, not everyone can, and you need to tailor your explanation to that. X-label steps. Show. All right, let's check this out. We have 5 steps. X value starts at 0, sigmoid is 0.5, and then check this out. Our gradient gets smaller and smaller and smaller and smaller. Let's try changing our number of steps. Let's change it to 100, and let's change X to 1,000. Here we go. So your sigmoid starts at 1. And it just immediately vanishes because the gradient is 0.000. Doesn't even fit on here, right? It's just a freaking straight line. Let's try with just 10. Just a straight line. This is exactly what I'm talking about. Where mathematically the gradient didn't actually vanish. It is just really, really teensy. Let's try X at 6. Boop. Gone. Gone in 1 step. It's over. You can always tell when it gets really small because you get these exponentials at the end trying to tell you exactly how small it is. So this is what I'm talking about, where RNNs within that sequence and multiplying by exceedingly smaller numbers makes it really, really difficult. There are a couple of things we've done to solve this. Different activation functions that are not a sigmoid. For example, a ReLU. How do you code a ReLU? We're going to say 0 if X def ReLU. Num equals 0, or let's just try this. If X is less than or equal to 0, return 0. Else, we don't even need that else. Return X. So let's do this for a bunch of numbers, like print ReLU -5. Print ReLU -1000. Print ReLU 6. 6,000. Right? Seems really easy, but it's one of the coolest ways that you can use to actually help mitigate these vanishing gradients, because you're not squishing it. You are still relegating things because machine learning has trouble dealing with negative numbers, especially in the inference, but you're no longer squishing things to the point of vanishing gradients. And that's not to say that ReLU doesn't have that problem. It's just that that problem is a lot harder to create in a ReLU. Okay, so let's get into the actual LSTM. LSTM.IPYNB, and we're going to be using PyTorch for this. I'm excited. I took a lot of time making this happen, and I'm going to add a bunch of stuff into our path. Copy folders. So we have our train folder that has labels and sentences. We're going to be doing some named entity recognition, which is actually really difficult for LSTMs generally because some of these can be longer. Let's talk about one of the main differences between an LSTM and an RNN. And fundamentally, they are the same. It's the same algorithm under the hood. The main thing is that LSTMs can be bidirectional, because we found out that only looking at things in the past of sequences actually doesn't help us, especially when we're dealing with language, where language is a lot more dynamic than just only looking at what appears behind us in a sentence. And even in languages like English, where your word order is incredibly important, what comes behind is just as important as what comes ahead. And because that word order is a lot less flexible, a lot more solid, essentially what happens is you can predict what comes ahead, especially if you're already familiar with what's being said. I don't know if any of you have noticed that as part of these videos, but I say similar things over and over again, and you can predict what comes out ahead. These are our NER tags. We're looking for geography, we're looking for organizations, art, time, person. If you're interested in this stuff, I highly recommend diving into some NER. Look at my hands-on NLP playlist. I'm going to be going over a lot of this stuff. This is a list of our whole vocabulary. And this, I'll just start coding and then I'll kind of get into what's going on really. So import torch. And we're not importing anything else. It's generally best practice to import only the thing you need from a given library. I want to show you where all of this stuff is located within Torch so that you can become more familiar even as we're doing this, because this is the last video, and so I want it to be really, really good and high quality. So yeah, that's basically that. Import numpy as np from tqdm, which this import tqdm. TQDM helps you visualize loops within a Jupyter notebook by telling you basically what you're on. Random. Import clear output. You don't need this. It's just to make sure that the output of a particular cell that we're going to be running doesn't get really, really long. And then this is probably the most important part, setting your device. We've talked in the past that machine learning requires a bigger device. In this case, a GPU generally helps for doing those matrix multiplications quicker. This will set your device to either a GPU or a CPU, depending on what your actual system needs. I'm going to tell you right now, going on a CPU, this is entirely possible, but it will take a lot longer. Torch.device, CUDA, if torch.cuda.is available, else CPU. And that took the linter a sec. Torch.manual seed 8855. And just to make sure, we're going to print device. And this will take a sec, but there we go. So we're going to be utilizing my GPU here. Ta-dum. So first off, I want to illustrate that you can just import an LSTM from Torch and use that LSTM, but there's a lot of stuff that goes into processing around it. And so if you just want to be done with this video and see how to use an LSTM.nn.lstm right here, and we'll just initialize it 1021, where 10 is the size of the vocab, 20 is the number of embedding dimensions, and then 1 is the number of layers that you're using. So if that 1 is, because it's a 1, it means you're using only one LSTM. Stuff equals torch.rand, we'll just do random matrix number. So we're just creating a random tensor here with these dimensions. The dimensions aren't incredibly important because the LSTM is ready to handle pretty much anything, any input. But then the output is just LSTM stuff, and it activates the forward function of that class, and then print output. Right? And then we have this tensor. And we have a gradient, that's this right here, the gradient function here, to measure that gradient. Because under the hood, this is still curve fitting. You're still trying to create a line that has decision boundaries within your data set. But let's get into, so that's it if you just want to instantiate an LSTM. We're now going to get into a bit more of like how to do real NLP, which I hope should be fun. So I'm going to copy this real quick. These are our target classes. Again, that's from this tags.txt. And we're going to get into creating an actual LSTM classifier neural network. So here we go. we'll set up some, I guess this doesn't matter as much, class Lstm Classifier. And this is going to inherit from torch.nn.module. As is the case with most of these, we're going to have an init function that is going to take self, and we're going to take an embedding dimension, and we're going to take a hidden dimension, and we're going to take a vocab size and a tag set size, which, if you've been counting, that's 17 here. And then we're going to instantiate it. Oh, we need self in there too. And then we're going to create our layers for this neural network. The first is just an embedding layer. Torch.neuralnetwork.embedding. So embeddings is what we've already been doing whenever we've been importing that CSV and mapping all of the essentially letters to numbers, or colors to numbers, or labels to numbers. And so the number of embeddings is our vocab size. This is going to be variable depending on the data set that you're using, and obviously the larger vocab you have, the better results you can get, but the slower the network is going to go. Embedding dimension is going to be 100. I guess we could, let's just do 50. We don't want it to be too crazy on here. No. I think the data set is actually going to require 100. We could do 128. That's a power of 2. Yeah, let's do 128. 128. Self.lstm equals, and this is the same thing, torch.neuralnetwork.lstm, and input size equals 100. And you're going to see the part of the reason I'm not doing variables for this is so that you can see, oh no, it's 128, we're doing that instead. That this embedding dimension is going to match the input size, because this is going to be the output of the embedding layer, and so we need the output to match the input of the next layer. Hidden size equals 75. That's going to be our hidden dimension. Oh shoot, I'm taking these. I'm just going to do this. Embedding, hidden dimension. And then num layers equals 1. We're just going to do it with 1. And then this last part, batch first equals true. Dropout equals 0.1. It's a 10% dropout. And we're gonna, right now, this is an RNN. But as soon as we add this in, bidirectional equals true. Now it's an LSTM. So congratulations. That's the difference. It's just that one variable, bidirectional equals true. And then the end of this, we're going to do self.dense torch.nn.sequential. And we technically could do this for the whole thing. I wanted to have the LSTM and the embedding be separate. Just for visual purposes, this whole thing could technically just be sequential. And you would just add in those to the... You would add in the LSTM and the embedding as the top two layers. And this is how you create a layer in it. Torch.neuralnetwork.linear. This is just a linear feed-forward network. Hidden dim times, and this, you'll want this input to be multiplied by the number of layers in here. So if you change this to 2, you want it to be a 2. Because ours is a 1, we're just going to keep it at a 1. Hidden dim, to try and get out of our vanishing gradient. Again, we're going to use a different activation function than a sigmoid. This one is going to be a GELU, which is like the ReLU, but gated. And we're going to do one more linear, hidden dim, and tag set size. So our ultimate output we want to be, we're going to have one dimension that is just a dimension, and then we're going to have one dimension that is every word of our sequence input, and then our last dimension is going to be the probabilities of our tag set. And in order to get that, we're going to do self.soft equals torch.nn.log softmax. Dimension equals 2, because we want it to be on that last dimension. And I'll show you what each of these do. Def forward. So this is what the neural network is going to do when we call it. Xbatch. We want I think I had this differently before. That's fine. So my I'm gonna have to update the actual reference that I wrote earlier. Self.embedding layer, and we're gonna embed xbatch, and then we are going to convert that into a float, and we are going to require our gradient. Oh, and you need this done, this underscore at the end of that. And then, output, and then an unused is going to be self.lstm. So the LSTM has a tuple output, where your first portion is going to be the actual output, and the second portion is going to be the weights from the hidden and the carry layers. And we don't technically need those for this. And then out equals self.dense output, and then soft equals self.soft out. Then we're going to return soft. This is technically not best practice to have different variable names for all of these, because they all could be the exact same, because we're just trying to manipulate the same data over and over again, and we don't want to overuse our memory. But for visualization, so that you can see what is coming out of each layer and what is going into each layer, I'm going to keep it this way. So let's see what this actually returns on a bit of data. Lstm classifier equals Lstm classifier. And we want our embedding dimension to be, was that 128? And then our hidden dimension is 75, and then our vocab size. This is a, what is our vocab size? $35181. It's words.txt. 35181. Perfect. Oh, and then we want tag set size, len target classes. Oh, and it was nice enough to import a random Unicode thing for us instead. And we're going to take a tensor that I've recorded from our actual data set in here. Input is torch.tensor, so you can see the dimensions that we're working with. And here is an important portion of this. Because we can't dynamically do these currently after it's already been instantiated, we want to pad our sequence to the same length. And this is a shorter sequence within our actual data set, but each one of these represents a padding token, just so you know. So print input.shape, and then out Lstm classifier input, print out, and out.shape. I'm going to multiply this by 2 times 2. All right, and there we go. So we actually do need that to be multiplied by 2. Interesting. Okay. So as you can see with all of these, if we were to index into it, so print out 0, 0. Where are you? Oh, here we are. So if we were to add all of these up, this is different from a regular softmax, which all of these would add up to 1. As opposed to that, this is a log softmax, so the range is from -infinity to 0. So it can be anything within that range. It makes it a little bit easier to work with these. So non-zero dropout expects num layers greater than 1. Oh. So yeah, when I instantiated this num layers was 2. So we're just going to delete the dropout because we're not using it. This is what it looks like though. Here are some helper functions that we've written to get our vocabulary and get our parameters for us. So the first one, get vocab, vocab path, tags path, and then vocab. If you're familiar with this, we're going to be creating a bag of words model for our vocab to keep track of it. There's a function for this called counter that you can use within an LTK if you don't want to use this function, but I kind of want to show you what's going on under the hood. Open vocab path, and the encoding for these, if you're working from the same data set as me from my GitHub, is ISO 8859-1. 8859-1 as our file for I, L, in enumerate, f.read, split lines. So for our index and line within this list, vocab line equals I. And this is basically just to avoid that ever being a 0. And then we're going to load our tags too. Vocab pad equals length of vocab. So we want the padding token to be the last token in our vocab. Which is, like I said before, 35180. So we're going to do the same thing with our tag map as we've done with our vocab. With open tags path encoding equals ISO dash 8859-1 as F for index tag in enumerate. You don't have to use the same variable names as me. Split lines, tag map of tag equals I. So this will essentially give us a vocab and a tag map that's a dictionary that allows us to input a given integer and output, or in the case of going one way, we're inputting a given word into the dictionary and getting the integer that is representing that word. This helps with memory. Vocab tag map. One of the weaknesses of building a vocab this way is it makes it difficult to mitigate human error with misspellings or colloquializations. We'll get into that in the hands-on NLP playlist, how to get around stuff like that. We're not going to worry about it right now. Vocab tag map sentences file labels file. Sentences equals an empty list. Labels also equals an empty list with open sentences file. I'm going to just copy this because it's the same encoding every time. So we'll have this on the clipboard every time. As F. So just to explain what we're doing, we're essentially going to replace each token with its index if that token is in the vocab. If it's not in the vocab, we're going to use an unknown token. This helps us process things that, because if it's not in the vocab, this is going to throw an error. And so we have to have a way to handle everything that's not in our vocab. It helps to have a much larger vocab, but this makes it so that we don't need that vocab to be constantly huge. And we're going to do list comprehension here. Vocab token, if token in vocab, else vocab unknown, or token in sentence dot split. And if you're familiar with this, this is us doing a word level tokenization. So we're not tokenizing any further. If you want to tokenize further, you definitely should. You can download a tokenizer from Hugging Face, from NLTK. You can create your own tokenizer. I guarantee you will get better results if you do tokenize things, especially if you learn about it. The main thing that you should get to know from this entire series is garbage in, garbage out with machine learning. Tokenization with NLP is probably the most important part, tokenization and embedding. If you fail on either of those tasks, you're going to get worse results. And even if you have a really great model that does its best to mitigate all of this stuff, if you are inputting garbage, that mitigation can only go so far. Yeah, please look into tokenization. I'm going to be putting out a video on it really soon. But sentences dot append s. And then we're going to do the same thing with our tags. And I am going to scroll down so that I can see what's going on here. With open, or our labels file, encoding as f for sentence in f.read.split lines. Don't say I never showed you how to open a file. Tag map, label, for label in sentence dot split. We're splitting on spaces. Labels dot append. And this should be intuitive, but the reason why we're not replacing labels with an unknown label is because this is supervised learning and we should not have any unknown labels within this paradigm. Return sentences, labels, length sentences. Perfect. So now let's use this and create a data generator that we can actually pull sentences from. And the reason we want a data generator, and we're writing our own instead of importing a data loader from someplace like Torch, is so that we can shuffle the data and make sure that it's a little bit more random. We're not getting the same thing every time. This helps our model actually learn underlying relationships that are a little bit less biased than if we pick which ones it gets to analyze, because we will implicitly have some bias that we add into it. Equal get vocab words.txt, and then, oh shoot, what happens if you press shift enter? I've got such big fingers that this is difficult for me. Tags.txt, t sentences, so these are test sentences or training sentences, t labels, t size. You should recognize these outputs from our get params function, vocab, tag map. And because these are the training sentences, we're going to grab these sentences and labels from the train folder within this. Sentences, and then we want the same thing, /train labels. Good. Let's print a couple of these. T sentences 0 so we can see what's going on here. For the record, this is a sports data set that we're going to be, a sports news data set that we'll be analyzing or trying to perform named entity recognition on. I can't type and do all this at the same time. T size. And then we're going to do the same thing with test sentences. Test labels. Test size equals get params. Vocab. Tag map. Test sentences. And then test labels. And for the record, this is what those look like. So this should not be a difficult data set to recreate with your own version, either from scraping something from somewhere or whatever. It's just each line is a sentence. That's it. Each line is a sentence. That's how it's split. And for the labels, it is for each word we have one NER tag. And that's it. That's the whole thing. So let's finish this. It's missing labels file. Oh, it's because I didn't add a comma. All right, so this is what our first sentence looks like after it has been tokenized within our bag of words model. If you want to even just do a little bit of improvement on this, you can use a continuous bag of words model instead of just this regular one and do some embeddings. I'll go over this in a video in my hands-on NLP section. And these are the tags for this. So if we actually print, or you know what, let's just look at it. Thousands of demonstrators have marched through London to protest the war in Iraq. London, Iraq, places. We're getting another one up here. And demand the withdrawal of British people, troops from that country. So this is a sports news data set. I know that's not a sports sentence, but it appeared in the news, so it's in this data set. So let's write our data generator. A lot of libraries, including PyTorch, have a built-in data generator that you can use, and if you want to use that instead, feel free. This is, again, just explaining what is going on under the hood so that you can recreate it yourself. Batch size, X, Y, padding. Shuffle equals false, verbose equals false. And we're going to add a thing at the end so that this can be a little bit more verbose. Let's just start here. So number of lines equals length of X. Lines index equals args range. Number of lines. So this is creating an array with the indices of the lines so that we can shuffle them to get that randomness that I was talking about. If shuffle, so if that shuffle equals true, random, this is the whole reason we imported random lines index. And we're not shuffling the actual lines, we're just shuffling the index for when they get called within the data generator. Okay, so with that, we have to add in some logic to track the current position that we're in within this data generator. So index equals 0. We're just going to start there. And while true. By the way, because we're adding this while true in here, this data generator will go on forever if you don't add some sort of logic into your training loop that will cut it off at a certain point. So please keep that in mind. No, this is right. Buffer X equals 0 times batch size. So these are essentially temporal arrays. They're for storing the raw data for a given batch. Buffer Y equals 0 times batch size. And the reason we're putting that 0 into a list is for this. Thing equals list 0 times 64. Let's just do that. Print thing. It duplicates it. So we're creating a buffer along each X and Y. And in this case, X is our data, this is our sentence, and Y is our label. They're the same length. They have to be in this. Max length equals 100. I think the longest one in this data set is in the 90s, but I haven't actually checked that. For I in range batch size, good. If index is greater than or equal to the number of lines, we're going to reset this to 0. Index equals 0. So we'll reset it to 0. And then if shuffle is true, random.shuffle lines index. Okay, so we're going to index into our buffer X. So I had to step away for a second. Now the camera has decided that I am bald. Anyway, let's get back into it. So we're at our buffer X, which is going to equal X indexed into the lines index, which is indexed into the index. And basically what we're doing is, so the current position is stored using the lines index, and that index is our current index within that lines index. So we're storing the X value at the current position, and then we're going to store the Y value at the current position, and then we're going to create our matrix, and then we're going to assign those values. It should be not too difficult to understand. Y, lines index, index. And then we are going to take length of X, then buffer X, I. Then we're going to do if the length of X is greater than the max length is assigned to length of X. This way we can keep track of the longest length item in any of our batches. And then we're going to increment our index by 1. Then now I gotta scroll down so I can see. Now we're going to big X equals np.full batch size max length pad. And the same thing, Y. We're just gonna copy and paste this. For I in range batch size. Xi is buffer X, Y, then Y I equals buffer Y, and then for J in range length Xi, and we don't have to worry about it because Xi and Yi are the same length. Equals X J Y I J equals Y. Oh, actually, yeah, we'll store the full label here. And then for K in range 17, if K equals Y I J, then Y I J K equals 1. Else I J K equals 0. So if you're not catching what's going on right here, this is creating our first index within our matrix. This is then assigning the values to that index. So the x of ij right here, this is each given word in the sequence that we're putting through our LSTM, and this y of ij is each given label. And then what we're doing is we're taking that label and we're one-hot encoding according to the index of that label within the sequence. And this is what we're going to be comparing our softmax to. If you're not familiar, a one-hot encode looks like this. So you have a list, and let's say it's 4 long, 0, 0, 1, 0. and our softmax coming out of the LSTM up here, each one of these is a list of probabilities that's going to add up. In fact, we could, let's do this instead. Instead of a log softmax, let's do a regular softmax. So these will all add up to 1. And so this sets up our loss to be really nice, because it'll be like 0.25, 0.3, 0.01, and then whatever else adds up to 100 there. The whole point of it, though, is it's making sure that each of these confidence numbers, each of these probability numbers gets as close to 0 as possible, whereas the big one, which in this case it would be absolutely wrong, gets as close to 1 as possible. That's how our loss is going to work here, or how that comparison will be working. And then back at this level, we want an if verbose. Well, we can just keep it on the same line. Print index equals index, and then yield. And this is the key to it being a generator function and not a regular return function, is we use yield instead of return. What this means is that each time we call the function, we're going to get a different thing, and we can for loop through it or while loop through it. It's an iterator now. X and Y. And then this is good enough. So let's then instantiate our train loader and our test loader data generator, and we want this to be batch sizes of 64. If you're running into memory issues, which you probably shouldn't for this, but if you are, decrease that batch size. We want sentences, and then we want labels, and then we want vocab, pad, it's in all caps, and then we want shuffle to be true. We don't care about verbose though. Test loader. We're going to do the same thing as this, but we are going to change the T to test in each of these. Awesome. And then let's just make sure it's working. In train loader, print x.shape, y.shape, and then we're going to break it. Make sure to break it, because if you don't, this while true is going to keep it going forever. Object of type int has no length. I did something wrong here. So let's run this now. Oh, did it restart? Yeah, the whole thing restarted. Okay, so let's run everything. Need to make sure we have our vocab, and then we're fine. And something you should notice is our out shape is 128.17. Max length, we need this to be 128. And then here we have our input and our label. And we want those to be exactly the same so that they can be compared nicely. And let's write those functions for comparison right now. We've got just compare model, loss function, and a test loader. And then we've got our width So this is our evaluation loop that's going to be happening inside our training loop. So that's why we're using this, the torch.nograd. It means that torch is not going to be keeping track of our gradients. We actually need to call it y shuffled. Yeah, we'll do big one just so we keep consistent. Y shuffled, y predictions, losses equal empty list, empty list, empty list. Iterations equals 0. And again, we're doing that to make sure that this while loop does not continue on forever. And the only reason that we're doing this is I want you guys to see how you can create this under the hood. I don't recommend that you do this. I recommend that you actually use APIs that are created for this sort of thing. Hugging Face has Trainer. PyTorch has Data Loader and Trainer. That they automate this process, but you should know what's going on underneath so that if you need to change something, you have the ability to. Test loader to do, and we want x equals torch dot capital T tensor x dot to device dot long. Perfect. And y equals torch dot float tensor y dot to device. So this is just converting our inputs into the type of tensors that they need to be processed by the various things. We need floats for our loss function, and we need a long or an int type tensor. So you could do int64 if you'd like for x to be processed by our model. So predictions equal model x, easy. And loss equals loss function preds y. And then losses dot append loss dot item, because it's a dictionary, y shuffled dot append y, because this is going to be shuffled, and we want to make sure that we can keep track of it after. Preds dot append preds. Iterations, iterate. What just happened? I do not like that autocomplete. If iterations is greater than the length of our test set, then break. And then y shuffled. Torch.concatenate y shuffled, and then y preds equal torch.concatenate y preds. Perfect. And then we're going to do some f strings, print f validation loss torch.tensor lowercase tensor mean. We're going to take 3 decimal places. And then in order to get our accuracy, we're going to create a mask. And it's essentially going to be y shuffled. And in order to actually do anything with this, we need to detach it. And we need to put it on the CPU. And we're going to convert it to NumPy. And we're going to do a character-wise comparison to vocab. Pad. So this is going to create a NumPy array that is essentially a whole bunch of true falses about whether or not each word or each word in this y shuffled equates to the padding, because both the x and y are getting padded to 128 tokens, and that we're then going to compare all the non-padding to see whether our accuracy is any good. Accuracy equals np.sum. We want the sum of y preds dot detach dot cpu dot numpy to do the comparison to y shuffled dot catch.cpu.numpy. We want to multiply that by mask. Then we want to divide that sum by the length of mask. Yes, I think that's right. Let me check. Oh, nope, it's not. By the sum of mask. Perfect. And then we've got our validation accuracy that we can print. Great. So there is our evaluation loop inside our training loop. And we're going to write the training loop, which is model, loss function, optimizer, train loader, test loader, and number of epochs. Epochs, epochs. I never know, because I learned initially about AI from Jeremy Howard, and he's Australian and says epochs, or I think he's Australian, he might be South African. But I hear Americans say epochs all the time. I don't know which is right. You can call it whatever you'd like. 1, because we don't want 0. Epoch. Epoch. Losses equal empty list. Iterations equal 0. For x, y in train loader. Oh, we're going to 2QDM this so that we can keep track of it. Model.zeroGrad. We essentially want to zero out the gradients for each loop here because we're going to keep track of them and we're going to use them to back propagate, and we don't want to overdo it there. I guess we could do optimizer.zeroGrad, but just make sure you only do one of them. Either do model or optimizer. And you guys already saw what we're going to do here. In fact, we could just copy this because it's the same. And then we're going to do loss.backward, and we're going to do optimizer.step. Iterations is going to iterate, and if iterations is greater than the length of our data set, which if you're wondering where I'm getting these, it's literally you just go to this file and scroll to the end, right? Same with labels. This is where I got the length of labels. Or, I mean, they're the same length. Same with test sentences, right? That's the length. But it's 3 through 570. Break. And then if iterations divided by 1,000 has a remainder of 0, then we're going to clear output weight equals true, and we're going to print our current loss. Train loss. Torch.tensor losses dot mean. Nope, that's it. And we're doing 3 decimal places. And that should be it. And then we're going to go to this for loop. Not all the way back there, but then we're going to do compare. Yep. We're going to give it our model, our loss function, and our test loader. And then torch.cuda.empty cache. So we don't want to overfill our memory every time. Perfect. So we have our definitions. We want to define how many epochs we're actually doing. I'm just going to do 1 right here. Loss function equals torch.neural network dot cross entropy loss. I would look at a couple of different loss functions. I'm going to do a video on them later. Actually, no, I already did. Did I? I think that I already did a video on loss functions with the first time I did MLPs. I did activation functions and I did loss functions where we went over mean squared error, we went over cross entropy loss. There are a lot of different types of loss functions you can do. This is a basic one for sequence modeling, like sequence to sequence problems. Lstm classifier is going to equal our Lstm classifier. We're going to give it our, we're going to look at exactly what we did before. Only we're going to put 17 in here instead. And you can assign all of that to a variable if you'd like. I just haven't. And our optimizer, which this is how we are determining where we move and where we take a step based on the gradient at the end of every single iteration. Not epoch, but literally iteration. Torch.optimizers.atom w. This is generally the best one right now. You can also, if you want to use stochastic gradient descent like we did in while true learn, which we can for this as well, we want to pass the parameters. And you can also give it a learning rate. I'll just do that right here. Learning rate equals 1e to the negative 3 is a nice high-ish one for our purposes. Learning rate equals learning rate. I guess it's just LR. LR stands for learning rate. Perfect. And then we're going to run this for one epoch. It's going to be terrible, but it'll be fine. This eventually converges at about like 75% accuracy because we've set up the problem for how to do NER basically. We haven't delved into our data set. We haven't done any sort of hyperparameter tuning. Something that you can do for LSTM classifiers that we're not doing is initialize it with hidden weights to make sure that it's processing things based on already computed weights. And you could do feature engineering, you could do feature extraction. There's a lot that we can do to make this better. I'm just gonna let you jump right in and start using it, so that, because a lot of this can become intuitive by just playing around with what's going on already. LSTM classifier, loss function, optimizer, train loader, test loader, and epochs. And oh, it's called training loop. Boop. Let's see, what error did we get? Expected all tensors to be on the same device. Nice. Oh, okay. So let's do this to device. And let's do this as well. Whenever we call the model, we want x batch equals x batch dot to device. And let's restart our kernel and clear outputs and then run all of it. Is it going? Oh, hey, this isn't running. We want dot to device here. Basically what's happening here, what this error is we have, and now you're saying device equals CUDA here. We want all of our stuff on one device, and right now it's finding the model on the CPU and the data on the GPU. And we want both the model and the data to either be on the CPU or the GPU, just one of them. So we'll restart and clear one more time. You don't have to. You could have just gone right through this, but I just want to see it all run, how fast it goes. Nice. So here we are. It's going at about 135 iterations per second. You can optimize this. You can get it up to about 1,000. I've seen it at about 900 iterations per second if you go through and optimize what we're doing or use APIs that are not Python, you know, that are written in Rust or C++. Torch is written in C++, and that makes it run pretty quickly, but we have other stuff going on as well that's bogging it down. It doesn't have to be this slow, but even going this slow, it's only going to take probably about it'll take several minutes actually. So I will come back when this is done. So we got 0 accuracy and a really high loss for both training and validation. It makes sense because we're only doing 1 epoch, but run this more and it should be better. If you want to save your model at any point, this is the API to do it, and then you just give it a name, Lstm NER, right? I already have a saved model, so I'm not going to do it again. Model equals torch.load, and then give it that same path. And then here is a quick function to predict using your own sentences, so you can see whether this is working, and you can try to make it better. This is a sentence taken from our data set, and it will print the word, and then it will print the softmax prediction of what's going on. Anyway, thank you so much. I realize this is a longer video, but it's the end of an era. There are a lot of things that we could do further to go into this, and I'm going to do other videos on those, on tokenization, on hyperparameter tuning, on actually deploying one of these models online so that somebody else could use it. Yeah, we're going to get into some ML ops. If you're interested in that, go look at my hands-on NLP playlist. There's already 3 videos there right now. And don't forget to subscribe. I really, really appreciate your guys' support. It lets me keep doing these videos. And for that, thank you, and have a great one.